Welcome. I am delighted to welcome all of you to one of the Dean's seminars. The seminar will be given by Howard Stone, and it's about the fluid mechanics of speech, which is very relevant to the times now. But before we get into the presentation, and I will say something about the Dean's seminar series, I have a sad announcement to make, and is one of our NAE members, Leon Kier, died unexpectedly yesterday night. Leon was one of the gentlest colleagues I have ever met. Someone really always at peace with himself. And I had a sort of special link with him. We were elected both at the same time in the National Academy. So Leon always was someone that I look a little bit differently than some of my other colleagues. But he was one of the giants in elasticity and mechanics, and there will be an announcement, and of course, we'll do something to remember him. But to the point of today, we have these talks when there is something that crosses boundaries. On the 26th, for example, we're going to have a seminar given by Ben Jones. Ben is one of our colleagues in Kellogg, has a PhD in economics from MIT. He was a Rhodes Scholar, but his first degree was from Princeton, engineering, aerospace. And he has written a paper that is the social benefits of innovation. And since we all work on that business side, we innovate. And the conclusions of the paper is that this is good. I wanted all of us to hear that, okay? But today's talk will be given by Howard Stone. He shared with me a little bit about the work that he was doing on the fluid mechanics of dispersion of pathogens. We all live surrounded by air. We don't pay much attention to what's going on around us until now, because this is the way in which COVID-19 propagates. And he has done, even if you cross the name of papers, I would recognize a paper written by Howard, because has a style on of his own. And I thought that the seminar today crosses real boundaries. It connects with speech, some linguistics. So I go way back when to Howard. I met him when he was doing his PhD in Caltech. And then he was on to Harvard, and then he did something that very few people in Harvard ever do, which is he left Harvard, and now he's very much at home in Princeton. So with that being said, Howard, the screen is yours. Thank you.
Thank you, Julio. Can you all hear me? And can you see the screen?
Yes.
Great. So it's a real pleasure and honor to have a chance to speak to you today. I'm going to tell you about some work my group started in probably around March, when the pandemic really became evident in the United States. It's a collaboration with a large group of people that has evolved. But I want to call out Manuk Abkarian, who's shown here in the bottom right with the orange shirt. Manuk was planning to do a sabbatical with me. He arrived in Princeton March 1st with his family. He's an experimentalist. We were planning to work on some problems in soft matter. The university really shut down, the lab shut down, and a consequence was that Manuk and I started to talk almost daily from our individual homes about what we were reading in the paper, and that led to us thinking about the airflows in speech. We eventually got permission for him to go back to the lab with a little help from one of my graduate students, since the labs were held at low density. And we then began to collaborate with Simon Mendez, who's shown here in the right, and different people in my group. And so this is a kind of a story of discovery for us as we think about the airborne spread of a virus due to your speech, or how you speak. So the virus is SARS-CoV-2. It causes this disease, COVID-19. So I'm going to tell you a little about what you normally don't see. I'm going to try to illustrate to you how you disturb the air around you. We'll say a little about one mechanism that might be related to drop formation, which happens when you speak. We'll try to image that. And then we'll try to show how some of these ideas tell you you shouldn't just be thinking about social distance, but you should also be thinking also about contact time. And there's a lot of work you can read, of course, about masks and other things. We have a little of that in progress. So the basic idea is, what role do fluid mechanics concepts play in trying to help you think qualitatively and quantitatively about airborne spread of a virus? And one reason I think this is an interesting question is it was largely unaddressed in the literature, as far as I can tell. And although you now hear a lot of talk about it, there's a lot more talk of and attention paid to the wonderful work by very good aerosol scientists, but not as much perhaps attention given to what people in fluid mechanics might have to say. So I'm going to show you, so if you now go away and start to read your email, the one thing this slide is going to tell you what I'm going to try to tell you. I'm going to try to share with you experiments so you can really visualize what's going on. So there's no discussion about what might or might not be happening in some cases. We're going to use simulations which reproduce many of the qualitative and quantitative features, and there's some simple models that help you rationalize what's going on. And we're going to illustrate to you both in the lab and by simulation that when you speak, you create conical jets in front of you that are effectively where all the exhaled air is that you produce. I'll remind you later that louder speech is known to produce more droplets. This is work just in the last couple of years from Bill Riss and Part and colleagues. And I'm going to try to tie this to what linguists know, which is that plosive sounds are sort of pressurized sounds. They produce small vortices, and these sounds these airflows can easily propagate 1 to 2 meters in a very short time. So it's not as if you're only disturbing the air a small distance in front of you. If you actually take a high-speed camera and look at how you speak when you have wet lips, you'll see that you can produce very small droplets just from the opening of your lips. That hadn't been appreciated before. Of course, if you can get rid of it, we found by just putting a little lip balm on your lips, and so long as you keep the saliva off your lips, that will reduce that. And from a public health perspective, and you should really be thinking not just about social distance, how far you are from someone, but how long you are in a given vicinity. And masks, of course, change a lot of what I'm about to say. So you have to also, recognize that masks play a big role in changing the fluid mechanics. And of course, there's a lot of this work out there. So there are many important ideas that others are talking about. I'll introduce some of that today, and I'm happy to talk to you about it afterwards. Okay, so if you want to get yourself in a perspective for how fluid mechanics research or research in general in public health help us understand things, I first want you to pay attention to what you can read in the press. So here it says, the most astonishing thing about the pandemic was the complete mystery which surrounded it. Nobody seemed to know what the disease was, where it came from, or how to stop it. And the disease may be transmissible before the patient himself is aware that he is attacked. Healthy persons often carry about in their persons the germs of disease, thereby unconsciously acting as a continuing danger to themselves and a menace to others. You can ask when this was written, and in fact, it was written in 1919, shortly after the 1918 pandemic was winding down. And that might make you wonder or be concerned or ask, how is it that in 100 years, we found ourselves in this challenging situation we are now, when the same words are being used and have been used for almost a year. I'm not a virologist or a public health person, but you can easily read about the number of different viruses that have entered human populations in the last 20 years. They're listed here, starting with SARS-CoV-1, a relative of SARS-CoV-2, and continuing to the present day. And I think what this should suggest, and I think others have written about it, is that we should expect more, and we need to think about that. Now, very unfortunately, and this is tragic, the upper right has the numbers of, as of yesterday, the number of cases of COVID-19 in the US and the number of deaths. Tragically, I gave a talk like this 4 weeks ago, and the number of cases on the slide was 17 million. I changed it last night. And I think it points out the very challenging nature of this situation we find ourselves in, where the air is a big participant in where we find ourselves. So if you wonder why this might be important, you could ask yourself, how does your speech disturb the air? What should you be thinking about? Whether you're talking to a friend in the hall or at a party, talking to friends at dinner, maybe, if you're talking to them at dinner and maybe you decide, you choose, maybe you're going to sit at a table at your home or at a restaurant. If it's at a restaurant, they'll do some social distancing, so they'll remove some people to lower the density. You might want to be asking yourselves, is this really helping to protect you either from each other, or of course, there's the room scale events as well. You could ask, how good is the CDC's 6-foot rule? You've probably been reading a bit about this. It's still their 6-foot rule. And you could ask yourselves, what are the personal decisions you and your friends and colleagues can be making to reduce your risk? Okay, so here goes the main part of my talk, which is how we got started. The airborne spread of the virus. And there's a huge literature, relatively large literature on this. Now, if you're a fluid mechanician, I should say, the majority of papers in fluid mechanics, which are very good papers, the great majority until recently for decades have been on coughing and sneezing. However, this disease is different. This disease, as you've read about, predominantly, or at least a large number of people who are involved in the spread are pre-symptomatic or asymptomatic. And this has been found, of course, in cruise ships, offices, choirs, etc. When I first started to work on this, we recognized very early on that this might be possible because there was, and other people recognized this because it was in the news, there was a case in Germany, shown here at the end of January, where a business person had been at a hotel working in a conference room with German colleagues. The business person returned to China a few days later. They felt sick on the airplane. And then several people that they had been in contact with in the hotel conference room got sick. My understanding, though, was that only people around the table got sick. None of the hotel staff that were handling dishes, handling water glasses, cleaning up afterwards, none of them got sick. It was the people in the proximity of the conference table. And you've, of course, read about choirs and other things, but there's also exercise classes where you breathe more actively, where there's been spread that's been well documented. Okay, so what all this says, and what I'm sure you're aware of, is that ventilation clearly matters, ventilation at the scale of rooms. That's a larger scale problem. I'm going to be telling you more about the local problem when you're in conversations in close proximity to friends, colleagues, acquaintances. Okay. Now, there's a lot of very important research in the field, both in elements related to public health and in fluid mechanics. I have 2 papers, nice papers shown here, that give you the idea of what people have done. There's been work that looked a little at airflow in breathing or sneezing, where they qualitatively looked at some of the features. There's work that's been done tracking coughs and sneezes, and very nice fluid mechanical studies of this. And if you want a nice survey, Lydia Barubia from MIT is a recent paper in the Annual Reviews of Fluid Mechanics. But in addition, there's been some attention paid to speech, not a lot, but some. And in the fluid mechanics world, there's a paper devoted to the sound of pa. Pa, the sound P is a plosive. A pa produces essentially a vortex out your mouth that I will talk about with you. And if you're a fluid mechanician or a quantitative person, or you're trying to ask yourselves, how long should you be in a certain environment? You want to know something about time. So if T is time, in the fluid mechanics world where you worry about how things propagate, you often get power law spread, so time to a power n, just in ordinary fluid mechanical flows. If you have a jet that starts, like you turn on a pressurized air spigot and have air flowing out, you often, the starting jet gets created with a distance changing as the square root of time. But if you're an isolated object, like what you'd call an isolated puff or an isolated cough, as this object moves away from its source, it has to conserve its linear momentum, and it propagates then as time to a quarter. So power laws will naturally come up in quantitative descriptions. But you could ask about speech, and I'm going to point out that speech has its own characteristics that, for whatever reason, as far as we can tell, hadn't been characterized. And I'm going to argue that in this, for asymptomatic spread of a virus, which is certainly this case, this is I want to argue is a very important thing to try to think about as you try to create safe spaces, or as you interact with people, safer things you could be doing. Now, the work in the fluid mechanics world and the public health world on airborne spread of disease goes back to Wells in the 1930s. There were lots of beautiful work being done ever since then. Here's an image taken in a paper from that time period. And at the time, they understood that droplets could carry the virus, so it was very important to try to image the droplets that were the carriers, and a lot of work was done on coughs and sneezes. And in fact, at the same time already, 70, if not almost 80 years ago, they were already characterizing the role of masks and how that limited spread and limited the number of viruses that came out. So there's a rich literature that you can go to. And there's a lot of work done to try to understand all the droplets and the droplet sizes that are the carriers of the virus. And here's a very important early reference, and Lydia Maraska, who's referenced here, also has a number of very good YouTube video documents that you can go listen to really learn more. And as I've noted, although I don't list them all, there's a large number of research papers that are in this field. Now, with respect to droplets, you should be aware that Bill Ristenpart at UC Davis has documented two features of droplets that are important. One is that different sounds you make, vowels or consonants, frigatives or plosives, those change the number of droplets you produce per unit time when you speak. And when you speak louder, you tend to get more droplets. So that's often mentioned in the public press, because you might imagine that when people now congregate at bars, if they are speaking, they're likely speaking louder. That not only affects where things go, but it affects how much is in the air around you. So I'm going to tell you a story about speech as a transport mechanism for droplets. You could imagine a large-scale room where there are turbulent air currents and things like that. And I should point out three references at the bottom that are important. Jose Jimenez at University of Colorado has a number of very valuable documents and talks that you can see talking about how a leading aerosol scientist helps us think about airborne spread. I've already mentioned Lydia Maraska and Don Milton, who have written recently also about airborne spread, and Martin Bazant and John Bush at MIT have tried to produce, as has some others, some guidelines for for room scale spread of virus, and including how long you might want to think about spending in rooms to minimize risk. I'm going to tell you not about the large scale problem. I'm going to tell you about the local problem that's at the scale of a few meters, you talking to someone. And you could imagine that the speaker might be carrying the virus. You don't know because they're asymptomatic, and you're in a conversation So you're a susceptible person some distance away. Now you have to think about how things are being carried towards you. That's referred to as the direct transport problem. And you have to worry about what carries the virus. Those are the droplets. I'm going to simply assume that there are droplets present. Now, if you read about this, people will tell you that the bigger droplets fall due to gravity and they fall out over some distance. But the smaller droplets, the aerosols, and there's some discussion about, what size range you should worry about to call it an aerosol. I'm going to ignore that. I'm just going to say it's clear they're small enough droplets that they stay airborne on the time scale of your conversation. They will be carried by the airflows that you create. And what are the consequences of that, especially if you're standing within a few meters? So I'm going to show you this with experiments and simulations. I'm going to, as I just said, assume that the aerosols are present. And you could ask, if what I'm telling you is what airflows are created by speech, what should you be thinking about when you're in some forms of social gathering? And I'm not going to try to make any judgments about things. I'm just going to try to tell you what airflows are doing, and then you can draw conclusions yourself. Okay, so if you're a fluid mechanician, you want to characterize the flow. So I have some numbers here. When you speak, the speeds are typically a half to a few meters a second. That's the speed. The kinematic viscosity of air, or the density and viscosity of air. And you want to calculate a Reynolds number because you want to know something about the airflow. The airflow comes from your mouth, so you can take a length scale, which is characteristic of your open lips, and you find the Reynolds numbers on the order of 1,000 to 10,000. And so you can expect that the flow will have some features of turbulence. And because you're speaking, it's also a time-varying flow. You pause, you say something, you listen, etc. So it has all the time-varying features. And because I want to draw a conclusion about aerosols and droplets, I'll just say that if the droplets are a few microns or smaller, and you calculate a dimensionless parameter that tells you how able the drops or the small drops are able to follow the flow, the Stokes number is small, which means that small droplets simply follow the flow to a first approximation. So when I show you pictures of the flow, you should picture small droplets carrying virus that are simply having those trajectories. We did this by getting access to the lab. I should say Manuk Karian and my graduate student Nancy A. They set up a laser sheet. We then often would fill the space with a Halloween fog, as it's used in the art and performing world. And then we would speak near this fog, and anytime fog droplets pass through the laser sheet, you would see their emotion. I'm going to show you a number of images that look like the picture on the left, which is a person speaking adjacent to a laser sheet, and where the fog droplets intersect the laser sheet, you see them. We do a form of particle image velocimetry called correlation image velocimetry to track the motions. And we follow a procedure of Adrian Bask and Phil Affenrud at NIST, who in the spring, around March or April, published a paper showing that if you speak in front of a laser sheet, you can often see little speckles, which is where the small droplets are crossing the laser sheet. So we also do things like that to characterize droplet formation as we do these kinds of things. Okay, so what do we see? So if you take a normal phrase and you speak and you use this Halloween fog to image what you speak, you can image some of the motions. There's always some background motion in the room. And I should say, this is what you see if you say, sing a song of sixpence. And the final vertical structure you see is the pence. So sing a song of sixpence. And what you see is that and the upper left, by the way, is the time scale. And what you see is that this image, which is the scale of a meter, when you say the pence, it carries all the air you just expelled in front of you over 1 meter within 1 second. And that might make you wonder about the World Health Organization's social distancing guideline of a meter. Now, if you're a fluid mechanician, you want to, or scientist or engineer, you want to characterize the time variation. when you first start saying something, the air is just leaving your mouth, but it's part of a continuous flow. Fluid mechanicians will refer to that as the starting jet, if you can see my cursor. And so this is a plot of distance. We'll call it L, think of a social distance, but distance from the speaker versus time. And what you see is that when you say different phrases, or in this case, just the phrase pence, that at short times, the data from different experiments on a log-log scale roughly has a slope of half. That I pointed out to you is what a fluid mechanician would expect of a so-called starting jet when the jet is just being turned on and created. But once it propagates past the individual, it propagates as an isolated object, an isolated puff, very similar to what a cough will do. There it has to conserve linear momentum, and there it propagates as time to a quarter. So at very short times, at the scale of individual phrases and at the scale of a second, you get these kind of characteristics, and you will get air that moves over a meter in on the order of a second. Many of us don't realize, most of us don't realize this because we don't see it. This is meant to help you visualize it. So these kind of features then are now what I want to say more about. Okay. I should say we then fell into the following path. Manouk's wife, Karen, knew a lot about linguistics, and she started to explain to us some of the features of different features of language, in particular plosives, which linguists have characterized very, very well. And so those are sounds like P or B or T or K qualify as plosives. There's a pressure buildup behind your closed lips, and when you speak, that pressure is released. And so here's a high-speed video of saying a phrase with many P sounds, many plosives, and you can identify each individual plosive as you say this: Peter, Piper, picked, a peck. And you'll see that the different phrases, the speaker is off at the right, each individual sound is producing a vortex, and those vortices will propagate. And you'll see again, at the scale of a second, the strong plosives will start to propagate out towards 1 meter. And you can see also they tend to carry the air in front of them and effectively push them forward. So if you average this kind of structure over time, what you tend to see is a conical region forming in front of you. This is actually a time average image of the phrase after you've spoken it, and color coded by speed, with lighter colors being higher speeds. And so this got us thinking that you're forming these conical regions in front of you, easily covering a meter in about a second or 2 seconds. And what are the features of these conical jet-like structures? And so we then turned to a colleague, Simon Mendes, also in Montpellier, and we wanted to try to mimic the head. So our original idea was, well, we'll call the head a sphere, we'll put a small mouth in the sphere. I think about as a little circle, but in the simulations, it has an elliptical shape, sort of the aspect ratio of your mouth. Now we needed to try to seed this flow with features of speech. And so we were aware that in the 60s, in the literature on speech, people had actually measured some features of the airflow, like the flow rate versus time. Here they had actually done it for Sing a Song of Sixpence, which is why I showed you that phrase earlier. So we digitized this flow. We added a breathing, smooth breathing part where you inhale. So we have exhale, sing a song of sixpence, breathe in, sing a song of sixpence, breathe in. And we use that as the initial condition for a numerical simulation. And we also did it for Peter, Piper, picked a peck. So a song with a phrase with many plosives. And what you see is if you do a typical numerical simulation of this type, is you have a very complicated time varying flow, but as you watch it develop, it roughly has the features of the conical jet that we documented experimentally. Now this is a 40-second simulation, and the line to the right is 2 meters. And so this is suggesting that air flows that are driven by speech out 40 seconds, if you're talking in front of your friend, will propagate easily 2 meters. and the structure is roughly conical. It turns out 90% of the blue particles here that are just labeled fall inside a cone, the total cone angle being on the order of 20 degrees. And that cone angle is precisely what you'd get in a fluid mechanics problem if you tried to create a quasi-steady turbulent jet, say water and water or air and air. It has all of those features. Okay, so you can do this for different phrases. You can do this for breathing, doesn't matter. The Reynolds number is always relatively high, 1,000 or more. And so all of these features, when you breathe, breathe heavily, breathe lightly, or speak, you form these conical jets and they propagate out. The first number here is distance. They propagate out in about 40 seconds. They propagate out almost 2 meters. It turns out the rougher jets, which are the ones with the more plosives, propagate a little shorter because they tend to be a bit rougher. But the takeaway here is that all these features look like the experiment, even though we only had a few of the features of the experiment, really just a time varying signal that was digitized from a flow rate. And so these are generic fluid mechanical features of speech. Okay, so I've shown you here this generic picture of speech. You now might want to think about what happens when you're speaking to one another. I have to be careful now what I say. The original image I had here was from an indoor event at the White House a few months ago following the nomination of a new Supreme Court justice, where there was an indoor event that turned into a spreading event, but those kind of images you can't display, since I understand they can't be copyrighted so easily. But in any event, here's a speaking event. Now, of course, it's outside, so that's good. Of course, if the wind speed is low, maybe that's not so good. Now, if you're a fluid mechanician, you want to quantify this problem. So if you call x the horizontal direction, the distance from the speaker, if the flow is being created by a constant source of momentum, so you'd say a constant momentum flux, which is a quasi-steady jet, which I told you is representative of speaking, then the speed varies as 1 over distance, where alpha here is half the cone angle. The jet is entraining air, so the cross-sectional area of the cone is increasing. It's a cone after all. And the flow rate is increasing because of this entrainment of air. And then if you ask yourself, where do droplets go? And you think that droplets are carrier of the virus, the number of droplets is conserved. The number that leave your mouth are the number at steady state that cross any given plane. And so the product of a concentration and a flow rate are constant, and that tells you that the concentration only falls off as 1 over distance. I'll say it now, if you're 2 meters away from someone, then you can expect 3% of whatever you breathe out of your mouth to envelop their head, and that's the air that they're breathing in if there's no other airflow around. Okay, but you can take this picture and ask, does it predict this time varying flow from a person? And so we took a phrase, I think this was Peter Piper picked a peck, but it might've been Sing a Song of Sixpence. We time averaged over each cycle, and we plotted the average velocity that you observe as a function of distance. The red curve is when you just did 4 cycles of saying this. The blue curve is 6 cycles. The purple curve is 8 cycles. And what you see is that this velocity distribution precisely follows, more or less, okay, precisely is too strong, follows the 1 over distance behavior that you'd get if you just said it's a quasi-steady turbulent jet. Okay, so that is useful for now quantifying different situations. If you integrate up this expression, velocity goes like 1 over x, and ask, what distance in front of you is contaminated in time t? You find that the distance in front of you from continual speaking of exhaled air grows as a square root of time, where a is representative of the orifice, that's your mouth. V0 is the typical speed that you're breathing at. That will go up if you're breathing heavily, like when you exercise, and alpha is the cone angle. And so you can check this idea numerically. Numerically, I told you in the fluid mechanics community, there were only 2 things. There were starting jets that were supposed to be true at short time, and puffs, which represent coughs and sneezes at long times. All our data for speaking roughly follows the square root of t. There's a starting jet that's square root of t, and then a quasi-steady momentum flux that retains the square root of t at long times. And you can take our experimental work and also do this. So the way we did this is you stand in front of a sheet, a laser sheet, you move yourself some distance away and you speak, and you look at when you see a signature appear in the laser sheet. And again, this data shows distance grows as square root of t. You might notice that at 30 seconds, you're out more than 2 meters. At 40 seconds, you're out more than 3 meters. And you might wonder then again about these social distancing guidelines that people suggest. And if you're curious, a direct comparison between the experiment and the simulation is pretty good. The pre-factor is within about a factor of 2 between these rough speaking experiments and the simulations. But other than that, they have all the same features. Okay. Now you might say that this is irrelevant because if you're in a conversation and speaking at one another, the jets collide, and therefore your own speech and features of the exchange will act as a safety feature. So Sandeep Saha and his student Nilakash Biswas and another student have started to work on this with us, and we've approached it the following way. We've taken the same kind of speech signals you've already looked at the bottom, and we have one person speaking while the other person breathes. We call that the SB interaction. And if that's when the S is for sing a song of sixpence, and we do the same for plosive. And we can then have you speaking at the same time or at different times. So we have some of that. But more importantly, people are different heights. And so we included displacement of the two mouths when you do this kind of simulation. And this is just a short story of work very much in progress. But the upper right is when the two jets collide because they're at the same height. And effectively, when they collide, they don't go much further than half the distance between them. In this simulation, people are 1 meter apart, and the speaking simulation is for 12 seconds. There's a little, when they collide, a lot of transverse spreading. You could imagine someone standing to the side. On the other hand, when you're different heights, the jet propagates almost as if it's unimpeded. And so after 10 seconds of speaking time, because you're speaking at different heights, and here we only color code one jet, I should have said this, because you're speaking for so long and they're slightly different heights, the jets propagate almost the entire meter as if they're unobstructed. Okay, so that's work we have in progress. Okay, so that should maybe get you thinking about the environment around you. What can you say about the droplets? So I'm now just going to make a brief remark about droplets. In the literature, in the aerosol literature, the public health literature, the fluid mechanics literature on droplet formation, there are two very rational hypotheses for where droplets form. These are the only two that I'm aware of that are written. One is the droplets form deep in the lungs and they're carried up by the airflow, and then they follow out with your speech, or they're formed in the liquid line airways that are in the upper part of the respiratory system. The airflow shears them off. They break off little droplets, which are carried out. People do this by breathing into a big apparatus, which collects all the stuff that comes from your exhalation, and try to do droplet measurements. And as I mentioned, an important feature from this work is, in addition to the droplet size distribution, is the fact that louder speech, more droplets. Okay, so we got interested in, well, what happens when you speak at your mouth? And so we turned a high-speed camera on the lips, and what you'll see is that there's at least one other mechanism for how droplets form, which is you have wet lips and your wet lips open. It forms a sheet of saliva, which rapidly breaks into filaments, and then the filaments are stretched by the airflow as you speak, and the stretching of the filament reduces the size of the filament, and the filament eventually breaks into droplets by some form of a capillary instability. So this idea gets tied to speech because the lips open, that's one time scale. The airflow stretches the droplets, that thins the filament and therefore lets it form smaller droplets. And so you can plot the length of a filament versus time. There's a short time scale, which is a constant opening rate. Your lips have opened at the scale of milliseconds. You can see this in the video. And then at some point, the airflow from your speech is stretching the filaments more. And you can see that this forms a wide range of sizes. Now, of course, the bigger sizes, the droplets probably settle very fast. The droplets are generally evaporating, and so they get smaller and form the little particles. And so we've tried to add this to the literature on drop formation in speech. You can try, if you're a fluid mechanician, to understand it. I'll just say, if you study surface tension breakup of filaments, what you find is that this problem is dominated by the rapid opening of your lips, so inertia should be important. But if it was simply surface tension breaking a liquid filament, the filament would break very fast, as shown on the right. Whereas our filament lasts tens of seconds, and that tens of milliseconds, and that time scale is comparable to the elasticity of a filament that has polymer in it. The polymer here being the mucin included in your saliva. And so this is a problem where there's a viscoelastic fluid mechanics problem that's helping stabilize the filament as it's being stretched, that eventually leads to the droplets I showed you. We haven't done much more on that, but than what I've shown you here. But you might want to get rid of it. And so what we noticed is, look, this happens when your lips are wet. Therefore, try to make your lips not wet. And one way to do that is put lip balm on your lips, something like that. And as long as your lips don't maintain a saliva film, you tend not to form droplets. Now, of course, you probably are aware that when you put lip balm on your lips, eventually your lips start to become wet again. But this is at least one way to reduce the number of droplets that forms when you speak. Okay, I think I'm sort of coming to about 5 more minutes, so I have one last slide here, and then I'll close with one other feature. This issue of surfaces separating is important for musical instruments. So if you take a saxophone, my friend Manu Kapkarian had his saxophone with him, so you use the high-speed camera and you look up the mouthpiece and you see the same kind of thing. As a reed vibrates against the surface, you see filaments being formed, which is the precursor to droplets being formed. And if you turn, if you find on the web images of the glottis opening as you speak, you see that it's really two soft surfaces that are touching. And so you can imagine this is also, and I think 1 or 2 people have written about this, a possible source for droplet formation when you speak. Okay, so with that, I'll turn to one last feature, which is what can you say about thinking more about the contaminated air that might be in front of you when you're in a casual interaction? And so you have this picture in mind that you're with a group of friends or if it's someone in your pod, maybe you're okay, but friends you think are, you know, trying to be safe, you're going to get together with them. You know that when you speak, you're going to form these conical jets. They have quantitative features. And the important ones here are that the speed varies as 1 over distance. The airflow that's being created is entraining air, so that's increasing. And that you exhale material from your mouth, and as it moves away from you, it's being diluted. So you can turn this into a model of local risk to say it's not just separation distance, but how long you're in a interaction. And there's a well-known model that goes back to Wells, which thinks about all the little viruses that might be infecting you, and each one is sort of an independent actor that might be the cause of an infection. And so there's in this literature, a probability of risk P, which is 1 minus the exponential of the number of virions that you inhale into you divided by some characteristic number that is representative of somehow, you know, some fraction of the people getting actually getting sick. And so this number NC has been estimated to be on the order of 100. That's a conservative estimate from a number of different groups looking at different cases, the Diamond Princess case or some other cases of transmission. And so we used our model to calculate if you're breathing near someone speaking at you and they're a distance L away and they speak for a certain amount of time, you breathe in a certain flow rate of air and you breathe in from someone who's breathing out a certain concentration of virus and a certain number of droplets that are produced per unit time, then you can calculate a little formula which relates distance and time and variables that affect that interaction. And you can turn this into a diagram qualitatively that you might call a risk diagram. So On the horizontal is distance, on the vertical is time. So situations that are less helpful to you are short distance and long time. Situations that are better for you are long distance and short time. And if you thought the probability of risk was 50%, you'd sort of get this solid line here. I don't think that's a good idea. And if you try to think about what these diagrams mean, there's a variable that you have to be aware of, that people have tried to estimate how much virus people produce. And there's a mean, but there's a big distribution and a tail with a few people that produce a lot of virus. In fact, virus that's at least 100 times more, if not more, than in this diagram. So I'll just point out that if you thought you were okay at 1 meter from someone to speak for 7 minutes, if they happen to be the more infective people, you have to divide that by a factor of 100. That's 4 seconds. That's just roughly saying hello, standing there and walking away. And if you wanted to base your risk on a 10% risk, then the diagram sort of looks like this. And so these ideas, I think, can inform how you go about interacting with people. Okay, we've done some work on masks. I realize I don't have time for that. So maybe I'll just skip that and just end with these last 2 slides. One hope sort of I have is that people are attentive, and maybe one value, maybe there's no value to what we've done, but if there is value, it's imaging and illustrating to people what they can't see when they speak. To appreciate that this might not be appreciated, I'll just point out that very recently there was a German news report. It had a very nice discussion of how to stay safe during this time where there's airborne transmission of the disease. And it was a very nice discussion between a reporter and a leading aerosol scientist. They wanted to show how to stay safe in a restaurant. So they went into a restaurant together, they put on masks, they had a very nice discussion, and then they walked outside. They walked outside and took off their masks and then stood across from each other and had a conversation. And you can decide for yourself whether this is a good idea or a bad idea. It's outside, so that's generally good, but only if there's a significant wind. So with that, I'll just say thank you again for this opportunity to give a talk. It's always a pleasure. I've known Julio probably my whole professional career, so I owe him many, many thanks. And I've had several wonderful visits to Northwestern, and I always look forward to them. But I've tried to tell you a little about the transport and airflows. I've tried to tell you a little about another way droplets might be formed in speech. I tried to highlight the space-time idea, and Philip Borean and others in my group have been studying masks, but also hosting musical performers from the Met Orchestra. So I'll just leave you with this, which is CO2 imaging with a camera from the Fleur Company of a mezzo-soprano, Isabel Leonard. And we're trying to understand now how professional singers and professional musicians can be able to perform. And there are several studies actually already on this as well. And I want to thank the NSF for supporting this and the program manager, Ron Jocelyn. And with that, I'm happy to answer questions.
Thank you, Howard. So the questions will be moderated by Nilesh Patankar.
Thank you, Julio. Howard, great talk. Thank you very much. So I would request attendees to start sending their questions. Some have already sent, so let me start right away. So one question, Howard, that comes up is how to organize how the jet comes with respect to different sounds. And one way to organize is frictive versus plosive. But even a plosive sound comes from different parts of the mouth. Like, for example, your P, B, T, K comes from, different parts of the mouth.
So I don't know the answers to all those questions. I've just written a proposal to try to get funding to try to connect this next step of the connection of linguistics to airflows. Pretty much everything we've done is what I've showed you. They're clearly important connections to be made, and we haven't done them yet. So I don't know all the connections of this. Where we have imaged, but it's really just one or two speakers, some of the phrases, you'll see that depending on the position of the tongue when you speak, some of the phrases go a little bit more down or a little bit more up. And the plosives I showed you often propagate much more horizontally, but some of that is associated with the position of the tongue and your teeth. And they're, I think, important questions asked. I don't know anyone that's asked them. We hope to be able to study this connection between airflow and linguistics in the future.
Thank you. And then the corollary of this is, are there certain languages that are prone to a more spread? Or
well, that is a great question. I'll just say two things. If you do a search on plosives and Chinese, you'll find a recent paper on plosives and Chinese. It's clear that people have been thinking about this. You can find two amusing videos, one in French, where people tried to remove plosives from the language and substitute other letters for the plosive sounds. It took the English a few months to produce it, so that started to circulate as well. But there's certainly some information about plosives in different languages, and I want to be careful with this because I think it's a little controversial. But in one of the papers on droplets in speech, at the end of the paper, it's a paper by Bill Rissenpart and PLOS One. The last paragraph of the paper mentions the spread of the SARS-CoV-1 virus in China, and commented that there were both American tourists and Japanese tourists. And I think the way it's described is the Japanese language has much softer sounds. There were many more Japanese tourists, but the Americans tended to be the ones who were the ones getting sick. And I think it's, I've read there's a little controversy, but there are clearly issues to think about what roles language might be playing in this. I'm not an expert. We started this in March, but I think it raises many interesting questions.
Thanks. One question is, could you comment on fossilized jet structure after the person stops talking? How does it dissipate? And how is it affected by normal mouth breathing versus nose breathing? So what I would say is, one of the things you gave was these puffs pile on each other that forms a structure. How much inhalation impacts it, and what happens in the end as it dissipates?
Okay, so when you speak out, so when you speak and when you breathe, the Reynolds number is high. So to a first approximation, when you exhale, that forms a jet. But when you inhale from all around you. This is the famous problem of the water sprinkler problem in fluid mechanics. When you're at high Reynolds numbers and you have a flow in or out, if you only believe the Bernoulli equation, they're reversible. But outflow forms a jet. Inflow comes from effectively some large angle around you. So when you breathe in, you're generally breathing in from all around you. When you breathe out without a mask, you're generally forming a jet. When you breathe out with a mask, that spreads things out a lot more. So it cuts off the momentum, it spreads out the angle, and it reduces the speed. The dissipation is not one we've looked at, but I think it would just be the dissipation associated with the decay of momentum in the jet, and then any residual background flow that is driving a weak turbulent flow at the scale of the room would tend to dissipate things.
Thanks.
And was there a third? Oh, and then of course you mentioned, or someone mentioned, nose breathing. Yes, nose breathing is important. It's a downflow. It changes the flow structure. It's not something we've looked at. So you could probably refer to our picture as maybe a somewhat conservative picture, but it certainly adds a further complication.
And in the context of this, what are the key features that make somebody a super spreader?
Okay, so I'm only, I'm sort of an amateur trying to read this world. So super spreading is used when there is an event where one person is the primary source of the disease, of spreading the virus to many. Okay, now what can do that? Well, one thing that could do it is there's a distribution. If you go and measure droplets from your mouth, and Julio does it and Amy does it, there'll be a distribution. You won't all produce the same number of droplets per unit time. So some people, there are a few people that produce many more droplets than other people. And then if you keep track of how much virus is in your saliva, there's a distribution. And a few people, this is documented back in May. I know this from a colleague, Scott Kemp, and Dick Garwin. There are a few individuals at the end of this tail who don't produce a factor of 2 or a factor of 4, but according to the data, a factor of 100 or 1,000 more virus than others. So those two features more than anything would dictate that the exhaled air is much more contaminated than normal. Then, you know, the soft speech versus loud speech affects it a little, but primarily it's those two features: number of droplets per time and virus per unit volume of your saliva.
And in terms of speaking habits, like if somebody speaks with different orientation of the faces, such behavioral changes, might that be?
Yeah, I think that could be very important. You know, I should say that when we were doing this, we didn't know a lot, but I would occasionally meet Manuk to talk about things. We would meet outside the lab. We would stand, we normally started 10 or 15 feet apart, and we were always having a conversation like this. We weren't speaking at each other. I would see him out of the corner of my eye and I would speak straight. And a few times I've gotten together with people at my house outside, and we sat next to each other and I spoke straight ahead. Those have to reduce what you observe. Those are small social things. I don't know how reproducible they are for others, but it's clear that what you're saying is important, that when you're in an exchange, you know, and that's why I don't like that dinner table picture. Yes, you take out people at the dinner table, but when you speak to someone, you normally look at them. As soon as you look at them, now you have a direct air exchange. So from my perspective, I'm not sure whether that's a good thing or bad thing, but to me, it was reducing overall density at the scale of the room. That's a good thing. At the scale of the local exchange, I'm not so sure.
And a couple of final questions. We are running out of time. So the production of droplets, you mentioned the lip thing, but the tongue might also create similar aerosol. Is that a possibility? And another question I want to ask is, a lot of focus is there, of course, on how it is sent out, these aerosols. Is it possible that a person might actually inhale their own aerosol and that might contribute into a deep lung infection?
Oh, I see. It's great. Let me start with the second one. So the first thing on the tongue, we have a paper in PNAS where we have one video looking at the teeth and the tongue as, no, I think it's in physical review fluids, as droplets are formed. It's just qualitative, but it's a good question that the tongue can affect just this formation process. But we had, or at least I had thought, oh, I don't have to worry so much about breathing in my own saliva, but you're pointing out that if it's starting in the nasal passage or the upper airway, is it possible that when you breathe in, you're actually causing a further infection? I don't know enough. It sounds interesting to think about. I don't know anyone that's asked a question like that.
Thank you so much, Howard. We have more questions, but I guess we are running out of time. I will let Julio do the closing remarks.
Howard, thank you so much for taking the time to educate us on this. It goes without saying that if more people had seen pictures of visualizations of air, singing, coming from language, people would have been much more careful about how they behave in public. But I'm delighted that you were able to be with us, and the number of people in this presentation was well over 100, reached up to 120.
Can I just make one last remark, because I saw it in the Q&A? Someone asked about masks. So I could say one thing, you know, masks matter, masks help. If you visualize masks in the lab, although you've seen a lot of qualitative imaging, if you visualize masks in the lab, the airflow gets out maybe 10 centimeters. So effectively you're localized. So, and you tend to be warm. And so you tend to produce a plume around you, and then it more rapidly mixes with the surroundings. So masks have a huge effect on cutting off direct transmission between people. I hope that helps.
Fantastic. Howard, thank you again. I do not know if there was anybody from linguistics in the talk, but I'm really interested in these differences among languages. You mentioned the Japanese and the English speakers, and there has to be some big differences. So thank you to everybody who attended this. And again, Howard, congratulations for a great talk.
Thank you very much for the chance, and everybody stay well and stay healthy, and hopefully our paths cross again in person pretty soon.
Thank you, Howard.
Okay.